So I am here to introduce Madison. I think all of you know her, so I'm not going to spend much time up here, but I love saying you're a volcanologist. It's just like the coolest work, I think. I mean, you get to work and, I mean, it's like it goes to the center of the earth, right? I mean, it's so cool that you have this, like, anyway, that you're in this system. I think it's really cool. But more specifically, I think we wanted you here because you do work in Yellowstone and you're an active member of the Yellowstone Volcano Observatory Consortium. And we're gonna hear what you do in terms of your studying volcanoes. But I think most importantly, she's got a really great group of students, undergraduates and graduates, that she's been working with for some number of years, so much that you almost forget who they are. For it's too long ago, right, Madison?
There was too many undergrads. I remember the graduate students.
But Madison does the work that, you know, in terms of community engagement, student engagement, research that, you know, I think is optimum for us as researchers. So in that way, I think you're a really good role model. So thank you very much for talking to us and that's it.
Cool. Well, thanks everyone for being here. It's exciting to see so many friendly faces. So as Liz mentioned, today I'm going to be talking to you about Yellowstone. So we in our lab group, we're called the Monster Lab. Yes, very exciting. It stands for Magmatic On-Site Storage Triggering and Eruption Research. The grad students actually had a logo making competition and we ended up with that one. As Liz mentioned, I'm in the Earth Science Department. I'm a volcanologist, meaning someone that studies volcanoes. And essentially, we have worked with numerous collaborators since about 2019, 2020 to study in Yellowstone. So this includes, we were funded partially from the National Park Service. We have a larger grant through the National Science Foundation. We're part of the Yellowstone Volcano Observatory, which I'll get a little bit into more details about what that is. And then we've also been funded through the USGS. So today I'm going to talk to you about what we've been doing in the park for the last 5 years. All right, but to start off with, here are the graduate students that have fueled a lot of this research. Their friendly faces here. Natalie Craig did her master's in Yellowstone and is now working on a PhD. Ray Salazar did his master's in Yellowstone, is now working at the Montana Bureau of Mines and Geology. Belle and Liv just started their master's, so more to see there. Bree's currently writing up their master's. That was also focused in Yellowstone. Megan's the one that got out, that she graduated and moved to California. She runs a laser ablation instrumentation over in California. Banaz is in the back of the room, stayed forever, postdocing here, very lucky to have her. And Stacy Henderson is also doing her PhD in Yellowstone. So an amazing group of people that have made all of this possible. And essentially, if you multiply this image by like 4, that would be the undergraduates that have contributed to our group. And I'll highlight them as we go through. So who am I? I was geologically born in the great state of New Hampshire on the East Coast. No volcanoes there, just the roots, the deep, deep roots of what those volcanoes used to be when essentially the Appalachians were formed and all of these different mountain ranges accreted onward. The thing I loved about my time in New Hampshire was that the University of New Hampshire was such a great place to be an undergrad. So much undergraduate research. And so that really fueled me to continue on to a PhD, where I got to study deposits that kind of look like this. So this is a beautiful example of a volcanic eruption. It's found in California, Central California. And so I did my master's at the University of Idaho, studying actually a volcano in South America, and then my PhD studying this as well as Yellowstone. And now I'm here. So the reason I was kind of brought here, one of the things that I love about Montana State University is that they pride themselves in undergraduate research mentorship. I think Liam and Jacob can attest to that, as well as being an R1 with great graduate students doing phenomenal research. And so to me, it's really important to train the next generation to be these scientists, to be able to answer these big picture questions. And so being here at Montana State has afforded me so many opportunities to bring students out into the field, whether training them as field hands, going on field trips. We've even done backpacking trips in one of our classes where we then did a mapping project. Overall, it's just been a phenomenal opportunity to essentially bring students into the field. All right, so what are we doing? Why do we go out there so often? Why do I make them hike 8 to 10 miles to go look at a rock? Right, and that's because volcanic eruptions are pretty cool, as Liz says, right? There's a lot of open questions. Why do we study them? Well, hopefully, it looks like you're sharing videos. Oh, whatever. So this is an eruption from Calbuco, Chile. And I love showing this footage because one, I think it's beautiful. It shows the power of these eruptions, showing this beautiful plume that is forming up in the sky. But also importantly, it's showing how scary it must be for the people that live at the base of this volcano, right? And that this is probably, hopefully not an everyday occurrence, but is a pretty frequent occurrence for something that is this, what I'm gonna call small, right? And so I've argued a lot in my career that these smaller eruptions, this is an eruption that would be like 1/500th of the size of some of the Yellowstone eruptions, benefit from more frequent observation. All right, so just like the weather where you can put out instruments and you can like look to see what happens, check your instruments, start to kind of figure out what your models are showing you. Smaller eruptions like this benefit from the fact that we can put seismometers on them. We can put gas geochemistry out there and start to be like, okay, this is what happens when we start to see unrest in these systems. These are the signals that we're looking for. But large volume eruptions, fortunately, we don't observe every day, right? We very infrequently observe them. And so that then poses challenges for understanding, well, what did they look like when they erupted? An example of this, I think nicely is shown by this. This is an ashfall map. So this is a map of where those plumes actually deposited material. Up on the left-hand side, which eruption is this? No. Vanessa is like holding her tongue. This is Mount St. Helens, 1980, all right? And the ashfall map, you see essentially how many people here were around at the time? Maybe a few of you. A lot of people, when I show this, tell me they have a bottle of ash in their like living room from this eruption. And you can see it has a nice plume, made it all the way over here. Dozens of people died during this eruption. It was really traumatic for the volcanology community as well as the people that lived near this. But again, compared to what a Yellowstone eruption can produce, it's a very, very small event. So Mount St. Helens was about 1 cubic kilometer, which is some made up number that I'm giving you. No, it's like a real number, just a hard number to picture. Whereas a lot of the eruptions from Yellowstone are hundreds to even thousands of cubic kilometers. All right, so again, the scale of what Yellowstone can produce is really unique. And it also, again, poses challenges for understanding, well, how did that eruption proceed compared to Mount St. Helens? And so there's several open questions when we're trying to study large volume volcanic systems. All right, so here's this cartoon. This is a very simplistic magma chamber, but I guess if I asked a lot of you to draw it, maybe you would draw a round blob like this. Typically, when we think of volcanoes, we always use the soda analogy, where if you shake up like a closed bottle of soda and you open it, it then explodes up into the air. Oftentimes, volcanoes are thought of these like kind of pressure vessels where enough bubbles and gas build up. You then have an eruption that proceeds, and then over time, potentially this leads to collapse. But for large volume systems, we have a lot of questions like how long does it take magma to accumulate to make such a big amount of material? And more importantly, why didn't it erupt earlier? Why don't we just continuously erupt these small volumes rather than build to these huge, large-scale eruptions? Are they triggered in the same way as smaller events, right? Does this model, this simplistic model, apply for a large volume system? And over what timescales do these systems evaporate? Something that we almost know nothing about because we never get to see them. In addition, we often envision this as a continuous process. So you might never have thought of like, how long does it take for a Yellowstone eruption to occur, right? Does anyone have a guess what they might think would happen? Days, weeks, months, years? So we often envision them as just once they start, they just run away, all right? And that maybe it just takes as long as it would take to get that much volume out for them to occur. But what if they actually had multiple vents, like all over a large area, or multiple magma bodies? Would that change how we envision how this hazard might evolve? What if there's a pause? All right, so for instance, Mount St. Helens erupted in 1980, had that huge plume. Then it, had some small events that summer, and then it stopped for multiple years. Then there was a period of unrest during those middle 80s. stopped again for most of the 90s, and then another period of unrest in the 2000s. For people that lived at Mount St. Helens, right, you like all of a sudden have gas concerns, so maybe you didn't go hiking between 2004 and 2008. Maybe you were worried about your summer home during that time. But if we fast forward in geologic time 2 million years, all of that would pretty much look like the same event. And so how do we separate out what happened in the past to understand what kind of impacts it would have on the future? And so most of our group is trying to figure out, well, how do we recognize and quantify these kind of complications in the geologic record? So here's just a map. Here, let me just get rid of its advice. From a paper we wrote a few years ago. These are all of what we call the super eruptions that exist in the world. All right, there's 14 of them. It's defined as 450 cubic kilometers of material being erupted. So again, Mount St. Helens was one. So just upscale that. And they're all over. They're mostly found around what we call the Ring of Fire. So that's the Pacific kind of subduction zones where the Toba in Indonesia, Azo in Japan, Wakamarvu in New Zealand are all these large volume eruptions that essentially can cause climate impacts. They can cause major disruptions into animals and plants. And of course, if we look at our very own United States, we'll note that we actually have 3 separate volcanic centers that had these super eruptions in the last 2 million years. Not to cause panic. Okay. So of these 8 host volcanoes, 50% of them, I think this is interesting, had multiple super eruptions. Right? So that includes our very own. This might not look super familiar to you, but that is Yellowstone. All right, here we go. So Yellowstone's had 2 super eruptions, the Huckleberry Ridge Tuff and the Lava Creek Tuff. But importantly for all of our sleep at night, these reoccurrence intervals is around 100,000 years. Whereas a small eruption like Calbuco might be on the order of every 10 years we see an eruption like that, or every few years. And so again, that brings us back to this point of like, well, how do we understand a Yellowstone magmatic system? How do we know what's going to happen in the future unless we really study what happened in the past? So that brings us to thinking about Yellowstone. So hopefully this is a map that is near and dear to your heart in that we live here, but it might have a lot of data on it that you're not used to seeing. So we're up here, right in Bozeman. This is Idaho. This is something called the Snake River Plain. And importantly, Yellowstone is thought to be fed from something called a mantle plume. So this is where we get started connecting down to the core, is that there's this thermal heat anomaly that goes to the core mantle boundary that essentially is imaged today underneath Yellowstone. So this is actually data from geophysical surveys that show us what's happening underneath the crust. And so we see that there's these thermal anomalies that are coming down from the mantle. And so the North American plate is essentially moving over what is a stationary, you could think of it as a torch, and it's essentially forming pimples of calderas or volcanoes along the Snake River Plain, going all the way back to the McDermott caldera. All right. So Yellowstone is kind of where we are today, but there's a long and rich history of this plume making its mark across the region. So that brings us to the modern day Yellowstone volcanic field. So Yellowstone is largely in Yellowstone National Park, and Yellowstone National Park is the first national park, so it gets a lot of hype for that. And before I proceed forward with kind of explaining the volcanism of the area, I always want to acknowledge whenever people talk about Yellowstone being the first national park, that there were people that lived here before the formation of Yellowstone National Park. All right, so for 11,000 years, indigenous tribes used Yellowstone for hunting and trading. And this group here is called the Tukadika. They actually lived in Yellowstone all year round, which if you ever go into Yellowstone in the winter is like an impressive feat. All right, and essentially the formation of Yellowstone National Park resulted in these original inhabitants being murdered or relocated off of these lands in order to make this park system. And it's something that we need to do a better job of acknowledging, and we are slowly moving that way. But a lot needs to be learned and unlearned in order to make progress here. And so one suggestion that I have, this is written by a white scholar, but he does a fabulous job in this book of highlighting that a lot of the stories that we have of this time of discovery of Yellowstone are from the white settler perspective, and that a lot of the information that we received about Native peoples was often falsified by that kind of point of view. So I think it's a good read for understanding this nuance between the discovery and formation of Yellowstone National Park, but also the murder of Native peoples that was happening at the same time. And with that, because in statements about acknowledging the lands that we are on, it's important to have actionable items that we are moving forward on. Here's a QR code if you want to learn more about the importance of naming. This is actually a big topic right now. But the peak on the left used to be called Mount Duan. This was a lieutenant who's best known for murdering about 300 Indigenous women and children, and they named a peak after him in Yellowstone. For over 20 years, people tried to rename this peak and got a lot of pushback. But recently, like a few years ago, they renamed it to Indigenous Peoples Peak. So that was a good win. On the right-hand side, this is hopefully maybe a familiar site to you. This is Hayden Valley. And Hayden is also renowned for his descriptions and discovery and collections that are currently held in the Smithsonian of his journey from the East Coast over into these lands. However, he was a big pusher and proponent that Native peoples were inferior and needed to be trained and re-educated by the white man. So important to think about what are these names that we use, especially in this region of the world, that are still causing harm to Native people that live here today. And with that, I wanted to highlight, Marcia gave me this suggestion. It's a nonprofit called Yellowstone Peoples. It's an initiative to not only educate youth into the native ways of Yellowstone and land management, but also to get natives more involved with management in Yellowstone, how they used to essentially manage the lands before they were kicked out and the Park Service took over. All right, so Yellowstone is this first national park, but of course it's also very well known for the fact that it has an amazing amount of geologic features. So it's huge. It's the size of Puerto Rico. So whenever I send students in there, I have to like keep that in mind that it's going to take us a while to remap this whole place. It has half of the world's hydrothermal features, which is I think why most of us go to Yellowstone, is these beautiful pools of hot water, where the other major features in the world are in New Zealand and in Iceland. Also areas where you have a lot of heat flux coming down from below. There's about 1,000 to 3,000 earthquakes annually in Yellowstone. And it's also home, in the volcanology sense, to the world's largest caldera, or one of the world's largest calderas. Right, so what is a caldera? Essentially, the idea is that if you erupt enough material from the ground, you leave essentially a pressure gap, and the top will then drop down, just like a piston into some oil or something. And so what are these large calderas? Well, essentially, if you've seen this map, you'll see these like large lines here. So these are the outlines of the calderas. And there's 4 calderas that we can view in our area. And if you've ever driven through Island Park, which I'm sure most of you have at some point, you're in a caldera. And it's a pretty obvious one when you're driving through that flat. And there's the Mesa Falls Highway, scenic highway right there. You can stop and see the caldera rim, which is really cool. But these 4 eruptions include the Huckleberry Ridge Tuff. It's the largest and first eruption. It produced this massive bad boy here. And then the second one, the middle child, kind of produced this baby eruption, fully over in Island Park. And then the most recent super eruption formed what we call the Yellowstone Yellowstone caldera. They've actually recently imaged this in Yellowstone Lake as part of a big lake project. And then I always like to highlight that there's a small baby, quote unquote, 50 cubic kilometer one that formed the west thumb of Yellowstone Lake. So that's why it also looks perfectly round, and that it collapsed and then filled in with water. So I'm going to be talking about a few more geology terms today. Apologies for those that are not rock enthusiasts, but hopefully you all are. So there's 2 main types of deposits that we largely talk about, and they're associated with things called ashfall. So those are falls that essentially singular pumices will fly out of the sky based on their density. And the other thing is called an ignimbrite or pyroclastic flow. And this is this ground hugging flow here that's moving downward. So this is an example again from Mount St. Helens, my favorite baby analog. And this produces deposits that look very different, but are found all over Yellowstone. So the left side is a fall deposit, and you'll see that there's like nice, beautiful grading here where you see sorting and layers. It's very pretty. This is all from a fall deposit. So this is falling based on density and distance from the vent. This, on the other hand, is what we call an ignimbrite deposit. these flows that come out. They're just jumbled hot messes of material. They're extremely dangerous. You've probably seen maybe footage of people that die from these when they come down big canyons. They're hot, they're gassy. They can be on the order of 500 degrees Celsius, right? So these are pretty scary features in comparison. And Yellowstone's got huge, huge thick beasts of these deposits. So this is the kind of work that we do in the Yellowstone Volcano Observatory. So how many people here have heard of the Yellowstone Volcano Observatory? Some of you have? Oh my gosh. Okay, well, the Yellowstone Volcano Observatory is essentially a consortium of different institutions. So we now at Montana State are one of the 9 in the Yellowstone Volcano Observatory. Others include the Montana Bureau of Mines and Geology, the Idaho Geologic Survey, the University of Utah, and we all together monitor Yellowstone. And the reason we're doing it in this fashion is, well, it's kind of an interesting twofold. So the last eruption in Yellowstone was 70,000 years ago. So in terms of pressing volcano needs for, Congress to fund, Yellowstone might not be high on that list, right? Compared to Alaska or Hawaii, where we have eruptions almost yearly. But the flip side of that is everyone cares a lot about a Yellowstone eruption, right? People call from North Carolina asking for their hazard map associated with Yellowstone volcano in North Carolina, right? This has a lot of media attention because of the fact that there's still magma underneath it today. And so I view our role at Montana State University as we're in charge of the geology, the rocks that are on the ground, the volcanic rocks, and essentially what they mean and tell us about this volcano. And this, of course, is a rich, rich history. The reason why we have these undergraduate field or kids here is because of the fact that Yellowstone in this region has over 2 billion years of geologic history. That we can walk over to the Bridgers and see apparently like one of the oldest rocks on Earth, as well as some of the youngest volcanism, right? We have fairly young modern rocks, and that leads to over 300 different types of rocks in Yellowstone, right? A lot of rocks. Everything that you're seeing here in pink and like kind of orange, all of that is associated with the modern plume. And then so 2 million years and younger, and everything else here is older than that, right? It has different history. Even there's an old volcanic arc here called the Absarokas, which some of you, we have Absaroki, you've probably heard of the Absaroka Mountains. This is like a 50 million year old arc. And importantly, this is my shout out to the IOE, is that this geology is what makes all these thermal springs have different chemistry, right? Like the different varied geologies and rocks are what waters then leach out different strontium concentrations. It's what leads to different microbe stability. And I've even had a student that looked at how the composition and of these waters impacts the teeth of the animals that will drink from and eat plants from different areas in the park. So I would argue that the geology is the foundation to the IOE in Yellowstone, right? And that we are leading to the different plants, the different animals, and the chemistries that we're seeing out there. So important to understand what these rocks are and where they're located. And so that is, again, what I view the Monster Labs role in the Yellowstone Volcano Observatory is, even though I would say this is the role that I think the community thinks I fill. I don't know how many people have ever asked you when the next super eruption is going to be, but I get this question constantly. So I even had a student come to my office to interview me about the overdue of Yellowstone volcano, even though volcanoes can't be overdue to erupt. And so we frequently have to figure out how to answer questions around why we are not worried about a next Yellowstone super eruption. That if it did happen, yes, you probably would die, but that is not going to happen. And I've even had people ask me like what road they should take to leave if unrest starts, right? So all of these questions are like, okay, this is explaining the importance of science communication with people about what are realistic hazards in Yellowstone. Another example, this is a paper, actually a study that was presented at a conference. Lots of words here, but essentially the point of it was that before the last super eruption, it only took decades to kind of reactivate that magmatic system. This popped up right around the time that I started here, as well as the park geologist. And I've even used this as an example of telephone at the Bozeman High School, because this is what the headline started with, and this is where the news took it, right? So Essentially, Yellowstone super volcano's nasty surprise, only decades to prepare for an eruption. All right, so we went from that it took decades to lead up to the last eruption that was 630,000 years ago to within a few decades, we're going to have a huge eruption that's going to kill everyone. And so I think it just highlights the challenge of science communication in Yellowstone because people want this story. I've had many people call me to do a documentary and they want this story. And it's hard not to talk correctly, not to give it to them. So I just wanted to emphasize something called the Yellowstone Caldera Chronicles. This is something that we put out every week as part of the Yellowstone Volcano Observatory. We've written probably 15 to 20 articles at this point. Banaz just submitted one to Mike this last weekend. And this is a QR code to the first one we wrote, which I had undergrads write during a field trip during 2019. And the idea is that we're just trying to talk to the public about one simple science thing that maybe we're doing in Yellowstone and why to trust us and what that really means about the system. So I'm doing one right now about ashfall. What is ashfall? How do we measure it, model it, and understand plumes? And I think that the Yellowstone provides a very unique opportunity to practice your science communication because people, again, are going to try to twist your words. And I've even been on news interviews that have gone directly from a clip of me talking about volcano science to then talking about, what was it, alien invasion? Yeah, it was definitely something about like extraterrestrial life taking over in our society. So it's like, okay, I've lost some credibility here. All right, so what do we do exactly? The first project that we got involved in Yellowstone involved remapping the entire park. And initially I thought this was a great idea. You know, the National Park Service funded us to do this work. Interestingly, all mapping efforts in Yellowstone are associated with an anniversary of the park. So the first maps that are shown over here, there's over 21 of them, were all created in the 60s and 70s during the 100th year anniversary. And then they decided for the 150 that maybe they should look at them all and see if there's any mistakes. So they wanted to create a higher resolution map. But what you might be able to see here is that there's several maps in this area, in this darker green, that are at a very different resolution than the majority of the maps. And so that causes problems when you're trying to stick them together. And so essentially, many of the maps don't agree along their shared boundaries. So what that means is that when you put them together, a rock on this side doesn't match what the rock is labeled on this side. And we refer to that as a boundary problem. And so in order to produce a new updated geologic map, which is used in resource management, infrastructure, hazard understanding, you have to address these. They're even trying to build a new road right now. And so right now the geologists are out there trying to map these areas. They found a fault that no one's really studied, so they're working on that now. But there's a lot of work to still be done. And so I'll ask you, how many boundary issues do you think exist? Anyone have a guess? Again, how many places do you think the rocks don't match on one side to the other? All right, think about it in your head. The answer is 450. Okay, so here's the same maps. Everything in red is where the two maps don't agree. You might notice, if you're an astute observer, that a lot of these are in those maps that are at the wrong scale. All right, so essentially before we can even make a new map, we got to fix all of these. So what do they look like? And I'm going to show you the worst example. This quad is horrible. All right, so this is the map on the left-hand side, and this is the map on the right-hand side. Shockingly, this is at a higher resolution, even though they refer to all of Yellowstone's rhyolitic ignimbrites as just Tuff. Like they don't separate them into Huckleberry or Lava Creek. And so we went on, this is where we went backpacking. We went over here and oh my God, it was a mess. We like immediately left and we're like, no, someone else is doing this. This is, we would be on a unit that was mapped as like an Absaroka and we were on like a lava flow and it was horrible. I mean, there's so many problems right here, but this is just an example of a boundary issue. And so Natalie Craig, God bless her, I brought her on to do her master's to fix all of these problems. This was like my first master's student. And clearly, well, I guess second, sorry, Banaz. You switched to PhD. But anyway, I think that this highlights that there's a lot of work to be done. And so one of the things that we've been talking about in the Yellowstone Volcano Observatory is that we need to have a meeting and try to figure out how to prioritize this work because of the fact that it's important for resource management. But Natalie, after 3 summers of field mapping, was only able to correct 68, I mean, it's an amazing amount, but 68 problems. So that means that we still have about 400 left to address. And some of them are on the scale of this, right? This is huge. This is a huge area. The other thing that you might be thinking about, and one of the challenges we really had with talking with all of our partners on this project, was that let's say you're walking to this boundary. It's very likely that you're going to find a rock that's not in the right place on this map. All right, and so this is what we call an internal boundary issue. And so essentially Natalie wrote a huge thesis of best case suggestions for what the park needs to do to move forward with these problems. But that brings us to an internal problem. So not only have we been mapping along all those boundaries, but we've also been working extensively in this area here called the Sour Creek Dome. It's just above Yellowstone Lake. And why we've been working here was because of a 2018 study where field geologist Colin Wilson, who's been studying the Huckleberry Ridge Tuff for 20 plus years, decided to check on every single place on the map that was mapped as Huckleberry Ridge Tuff. So he hiked into this. It's no small feat. Just to get to this dot here is about a 7-mile half off trail through a swamp. You lose some students. That's when we started learning a lot about electrolytes. But anyway, so he hiked out there, and his field notes, because he writes detailed field notes, are kind of like, I have no idea what this is. This is not Huckleberry Ridge Tuff, nothing like what I've seen before, but I have no idea what it is. So he sent it in for a technique called age dating. So this is in geology how we know how old the Earth is we send in minerals, figure out how old they are. And essentially, these two ignimbrites that were mapped as Huckleberry Ridge Tuff came back to be Lava Creek Tuff in age. All right, so who cares? What does that matter? Just take all this purple, make it green. Well, why it matters is that it doesn't look anything like the Lava Creek Tuff as we know. It's very, very distinctively different. And so what that could suggest is that this eruption is longer or has multiple vents or different magma bodies. So there's all of this kind of what is happening here kind of questions that come up from this observation. And this, all right, so this is the most geology slide I have. So I've tried to make this as simple as possible. So bear with me. So, but one of these two ignimbrite chunks, and that's here. Does everyone see that looks like a chunk of rock in other things? This is what we refer to in geology as a breccia, right? So a rock that had a pre-existing life that was then ripped from its home and then taken in to be a new rock. But the important thing is that one of the LCT age dates that came back is this chunk. And so what that suggests is that you had to have an eruption, it had to cool, and then you had to rip through it in order for this beautiful outcrop over here to come out into the earth. And so what that suggests is a major time break in this eruption, that this eruption didn't occur within a week. In order to cool an ignimbrite, we don't know how thick it was, it would probably take on the order of months. And so this suggests for the first time definitively that the Lava Creek Tuff wasn't just like 2 months and then the whole thing exploded in a week. It suggests that this thing occurred over really long periods of time. It also suggests that it needed to have this kind of ripped up material, that you need to be near a vent because you can't transport these big chunks very far. And so that also has implications of where our caldera boundary is drawn, which is important for understanding, again, where are the future vents going to be if Yellowstone starts to show and rest. So this takes us to Sour Creek Dome remapping. I don't think any of you have had too much trauma in here, so I can keep showing all this. But essentially, we've mapped in this area for probably, I don't know, 17 weeks of time spent back here in this backcountry. The Park Service lovingly refers to this as a bear corridor, which is why they won't let us backcountry camp in here. Lots of bears going through this region. But essentially, this is the original map with the Huckleberry and some Lava Creek. And over here, what you'll see is that all the Huckleberry is gone. But importantly, we started actually finding new units of Lava Creek Tuff, not only the ones that were previously described, but just continuously finding more and more. And all of this was work done by Ray Salazar, as well as Haley Finch, who did her senior thesis on this and is now at Central Washington. And this is what I needed help with. I asked Ray this morning to help me remember all the field hands. These are all the undergraduates that went out with us over 3 years to help with this work. many of which went on to do research projects with us. Logan's a co-author on a paper with us, or working in different, like Henry's at the Montana Bureau. Two of these were REU students and are now in graduate school. So it's been a really rewarding experience to work with all of them, even though I don't think they would say the Sour Creek Dome was a rewarding experience. I mean, physically or emotionally, maybe. All right, so what do the rocks look like? This might mean nothing to you for people that don't look at rocks very often, but essentially the idea is that all four of these are different. This first one, most of the difference is that they're found in this breccia deposit, so it has a different origin. The cool thing about this unit 2 and why it was mapped as the huckleberry is it has these little black blobs in it that are actually scoria. They're mafic. They're like a Hawaii style composition that's never been found in the Lava Creek Tuff ever before. And it suggests potentially that there was like a deep feeding recharge event into the system. That's why we were like, what the heck is happening here? And then this unit here is interesting, is that it was mapped as a lava flow down in the south part and associated with a different eruption, but it's actually just a really, really intensely hot ignimbrite with really large crystals. And so it's very different. And currently right now I have 3 or 4 undergrads helping me describe the 140 rocks that people have collected in this dome over time. And then the last unit, which I think is my new favorite, you can see here that there's big chunks of stuff in it. This is actually, again, recycled ignimbrite of LCT age, again, suggesting that you're near vent, you're ripping up, you're essentially having these ignimbrites go out, and then you're ripping up new material. But importantly, this one is at the very top of all of the units. So stratigraphically, it has to be the youngest. It can't be associated with like that breccia. All right, so one thing I wanted to highlight, so over here, for those of you that haven't ever age dated a rock, this is a sanidine crystal, and these are zircons. So you may have heard of zircons, because zircons essentially what we use to date the oldest rock on Earth. And essentially you take these minerals out of these rocks and you can use radiogenic isotopes and you can come up with an age. And so when we do that for all the units in the Sour Creek Dome, we essentially find that they're the same exact age. However, we know from fieldwork that there's pauses, that there's like breaks within this eruption. And so that suggests to us that even though in age space, this is all the same event, we know that these are longer periods of breaks between everything that is happening. And so it highlights the importance of fieldwork when trying to understand how these eruptions proceed. I also mentioned a few times this idea about the fact that there's a lot of ripping up of clasts happening in the Sour Creek Dome. It's really unusual. We don't see this other places. And so it was first proposed by Wilson that potentially this suggests that the caldera boundary needs to be much more inboard western of where it currently is mapped. And so the reason for that is that these deposits are pretty far west in the dome, but they couldn't have traveled from where the caldera boundary is, which is over 10 kilometers away. You need to be much closer than that. So it either suggests that the caldera boundary is over here, and this is a wrong one, and it's actually reutilizing the old Huckleberry Ridge Tuff caldera boundary, which actually makes a lot of sense to me. Or it's a nested caldera, meaning multiple collapses are occurring, and that it's not just one boundary, but multiple. And that's what we're trying to investigate and write up right now. But I would argue another reason why that this might actually be a major structure. One is that if you look over here, this is where the Yellowstone River is, right? So oftentimes rivers exploit things we call faults, major weaknesses within the earth. So that's one piece of evidence to suggest that there could be a structure there. And another comes from gas measurements. So this is a map of helium gas within Yellowstone. So if you've ever heard, I don't know, how many people in here have used this? I guess, Laura, you've collected gas. But essentially the idea is that the higher this number is, the more it's suggesting of mantle helium, helium-3. Whereas as this number gets lower, there's more crustal helium, helium-4. And so what this is suggesting is that, again, if we look right over here on the western side of this dome, that there's essentially a deep pathway of material coming up from deeper in the mantle, to me, again, suggesting less crustal influence, maybe a structural weakness. So we're going to be arguing for an alternative, at least inward caldera boundary for what is currently there. All right, so I'm just going to end today with trying to figure out, well, where do we go from here and why does it matter? All right, so we now have all these new units in the Sour Creek Dome, but how does it fit into the major eruption of the Lava Creek Tuff? Because there's no original material in the Sour Creek Dome, so we have no idea how this, is it earlier? Is it later? How does this relate? And so the only approach we could think of to do this, since we can't look at contacts in the field, is to use geochemistry. And so this is just a smattering of locations that we have visited. And my student, Stacy Henderson, who's actually giving a talk in this room tomorrow at the same time about this, is essentially gone around to numerous locations, 40, 50 plus locations around Yellowstone, to collect rocks to try to figure out, well, what is the main foundation that we need to insert the Sour Creek Dome into? So what that requires me to do is to teach you just a little bit more about the Lava Creek Tuff. Most importantly, that this eruption occurred 630,000 years ago. I think you saw that from all of our ages. But importantly, it's been broken up into two members, A and B. All right, it's very simple. Just like Huckleberry is broken into ABC, Christensen, the original mapper, really liked these simple member ideas. And the idea is that one came out at first, A, and this has a mineral called amphibole in it. And then B doesn't have amphibole in it. So simple, just mineral difference between these two. And there's some kind of morphology differences in the field. So essentially we're like, okay, well, how does the Sour Creek Dome fit into this A-B stratigraphy? Well, that required us to understand a little bit more about what is A and what is B, so that we could look at any rock and be like, you're an A rock, you're a B rock. That's what Stacy's been trying to do. So this is just an example of all these minerals that are associated with this eruption. And Christensen, the original describer of this, said, well, quartz is the most abundant and sanidine is the second. And when we looked at all these rocks, we're like, yep, checks out, definitely see that, so that's good. However, he also said that A has amphibole and B has pyroxene. What do we see on this chart that's missing? Anyone notice? Amphibole. Okay, there's no amphibole. We can't find freaking amphibole. All right, so we looked at so many thin sections. We've only found amphibole in about 3 or 4 samples out of like 180 samples, even more if you include the Sour Creek Dome. So 300 samples looked at. Amphibole has been found in 3. One in Tuff Cliff, which is near Madison Junction. One that's outside of the park, but it's in mapped member B, so that's not really useful. And so all of a sudden we're like, is this amphibole thing hold up? What was Christensen thinking? And you have to respect the founders of your research. So we're like, okay, Christensen, what were you thinking? Like, we couldn't talk to him, but because we have this relationship in Yellowstone Volcano Observatory, the USGS mailed us all of his thin sections. So the actual snaps of each of the rocks that he looked at to make this original map. And we're like, well, where did the amphibole come from, Chris? Gotta know. All right, so the best sample from Christensen's collection that had beautiful amphibole in it, so glassy. I was like, how did we miss this after 2 years in the field? Came from this location in the Gibbon River. And so back in the day, the old road actually went along the Gibbon River before it went to where it currently is. So he clearly just grabbed the sample off the side of the road. So we got the GPS point, we went there, we found this outcrop, and we're like, oh gosh, there it is. And essentially, Stacy just did this. God bless her, I didn't even know. She sent it in for age dating, and it came back with an age of 787,000 years ago. Not the Lava Creek Tuff, all right? So this was pretty big to us. This was like the final nail in the coffin that amphibole cannot be used to describe A and B. We really don't have a lot of good tools to describe A and B. So we started to lose a little faith there. But excitingly, this is part of now the Mount Jackson Rhyolite series. All right, so what is this rock? Well, the Mount Jackson Rhyolite series are these intercaldera forming lava flows. And if you look up here, I know you might not be able to see it, but these rocks are all Mount Jackson. They're slightly older than the Lava Creek Tuff. But importantly, there's nothing that falls into the 780,000 year. So we may have a new eruption that we found by just dating this rock. The other important aspect of that is that they mixed it up because this is an explosive eruption. So this is also suggesting there was an explosive event between the major caldera cycles, where usually we just view them as lava flows, so effusive events, things like a small flow coming out. So this has big implications for our hazard map. It has big implications for the Lava Creek Tuff. And so new student, Liv Wheeler, is coming in. She's going to be mapping this summer with some field hands, essentially to try to understand what is Lava Creek Tuff, are we missing more units, and can we find more locations of where this unit is? Moving onward, other locations, this is kind of a reoccurring theme, which I think is really good for our undergraduate students to see, is that there's a lot of work that we can still do in Yellowstone. So here's an example from Flag Ranch. You'll see the fall deposit and the ignimbrite at the top. So nice sorted flow, dense material on top. And you might also notice this. So this is how it was on the map when we went here. This is a locality just south of the park. It was just listed as unknown ignimbrite. So as a scientist, you're kind of like, well, we should probably know what it is. So we took a sample to date. That was my response. Colin Wilson, an amazing field geologist, was like, there's no evidence that there's a break here. This looks like it's exactly the same unit. And so we sent it in for date, and what age do you think it came back with? It wasn't 780, 630, Lava Creek Tuff. It's also Lava Creek Tuff. So we just found, well, we now have evidence to suggest that this is also the Lava Creek Tuff. And I just want to highlight another master's student, Bree. So what Bree did was really interesting is looking at minerals throughout this deposit. And essentially what they found, this is just an example of something that's experienced high heat. And this is an example of something that has cooled quickly from falling out of the sky. And what their research has found is that there's high heat impacts on these melt inclusions at the bottom and at the top, but less so in the center, suggesting that both of these ignimbrites were hot when this fall deposit was kind of in place. And so that tells us that this package, unlike what we saw in the Sour Creek Dome, came out really quickly, that everything kind of came out and continued going, and that this is a unique package. I'm not going to go into any complication of that. So exciting to see. All right, so these are my last few slides, I swear. So the bigger picture, how do we move forward? So Stacy's actually using another one of those minerals that you can use for age dating called sanidine to reconstruct the Lava Creek Tuff. And so what this is just showing is each of these can be thought of what is the composition of this rock that I'm looking at. And the more similar that these peaks are, so your eye might be drawn to the fact that these peaks all look kind of more similar to each other, means that they probably came out of the same magma body, right? That this was crystallizing magma and they came out with this composition, whereas some of the other ones have much more complicated spectra that you're looking at. So importantly though, if you're looking at the sides, you can see that this one mode is actually mapped A and mapped B, but they're all essentially from locations up here. So what this is suggesting to us is that A and B don't make any sense. Like we can't reproduce them at all. And so we're writing a paper right now that says, no, let's not use A and B, but instead let's maybe build a model that it uses the data that we have to understand like, okay, maybe there was a vent near here and a lobe of material went out that all had the same geochemistry. And as we continue to do this at more locations, we're hopefully going to be able to use it to understand how the Sour Creek Dome fit into the whole structure of everything. Interestingly, as you go further and further away, some of these are really, really complicated, and they're all from really distal locations. So we essentially need to use statistics to try to understand how many magma bodies is this representing associated with this eruption. And again, trying to bring this back to big picture. I don't know if people have seen this, but this is a recent Nature paper that just came out in January. Any guesses as to what this is? Not Banaz, because you read the paper with me. Liam? Oh,
The mantle.
a mantle plume? Well, look at the depth. 10 kilometers-ish, not too far down. Liam, do you want to guess?
It's the caldera.
Caldera. So the caldera boundary is probably this black line. So you got one thing. This is essentially the magma that is currently imaged, the melt underneath Yellowstone today. All right, so this is a recent paper that came out. They used a new process to discriminate that there's separate melt lenses, none with enough melt together to actually erupt, but essentially showing that there's a significant amount of melt and where that morphology of that melt is. They also argued that a lot of that is actually moving towards the northeast part of the park, more so than like where magmatism has come out before. And so the importance of this is that we are trying to build something similar for the Lava Creek Tuff. We're trying to understand how many magmas were tapped, how they were tapped around this caldera, and how that might relate to what we're currently seeing today underneath Yellowstone to better understand how do these melt lenses come together? What's the timing of that? And using the things that actually made it out of the crust allows us to understand what we're currently seeing in geophysical space. And so I'll just leave you with what I left the USGS with, because not many people are mapping in Yellowstone, even though I hope that I'm arguing that there's a lot of issues that we need to be focusing on. But Yellowstone is the first national park and one of the few active caldera centers in the United States. We should know what rocks exist in its boundaries. We should know the location, the frequency, and the volume of eruptive episodes. This is important for hazard mitigation, resource inventory, and disseminating information to the general public, as well as the fact that there are scientists, known papers where people have gone and sampled something that was the wrong thing, and then they present information that might have this big interpretation, but it was not even the correct rock to interpret. And so I think this is really emphasizing the need for at least our larger community to come together, resource managers, different geologists from different areas, and figure out how do we move forward with this, especially with limited resources for actually doing this kind of work. And so I'll just say that I've had an extreme pleasure working with all of the students on this project. And we have worked really hard to also address other important aspects of being a geologist, including that the true cost of field education can be really challenging for not only diversifying the geosciences, but other field-based sciences. In addition, a lot of people might not see themselves as someone that wants to go out into the field. And so how do we break down these barriers for what it means to be an earth scientist in today's times? So we spent a lot of time thinking about this, and I just want to highlight a few things we've done. So one year we had a volunteer field hand training experience where people could choose front country camping, back country camping, 1 week of experience. It was a lot of work for the graduate students, but we involved maybe 10 to 20 undergraduates in these small experiences, and I think it was really impactful for them to gain their confidence in themselves to be able to do this kind of work. We've also created a Lend-Lease program for field equipment in our basement that allows people, our students or faculty, to borrow different kind of equipment, especially tents, for instance. So when they go out for these experiences, they don't have to buy those things themselves. And we've also created a bystander intervention guide for our trip leaders to facilitate conversations about safe and inclusive fieldwork. And this was based on something that Diana and I did together many years ago. We had a bystander intervention and field safety training through Advanced Geo. Essentially, the important aspect of this was, using the iceberg analogy. The big message is that harassment doesn't have to be illegal to have damaging consequences. And so we talk about what are the ways in which things that people could do could be perceived as offensive, and how to find your voice to be able to either intervene if that scenario happens, or know your resources to make sure that you feel safe and protected in the field. And we used a lot of this. This is a last QR code of the day, but this was a report on field safety kind of surrounding ships in the ocean. But the nice thing about this field safety workshop report is that it breaks down everything by how much money it costs to implement, as well as how much time it takes. So you can go for that low-hanging fruit to begin with, and then build up to start to tackle things that are going to take more time or more money to implement. And so we've used a lot of this in creating our own guide. I know we've shared this guide with different resources on campus that who knows where that is all going, but I think it's important, or at least it has been important for our group, for people to feel safe and heard while in the field. And so with that, I'll thank you for your time and take any questions.